Hello, good morning. So welcome you again to this World Large River and the Delta System Source to Sink webinar series. So today we invite Professor Albert Kettner to give a talk about changes in fluvial system supply to global perspective. So before I introduce Albert, so let's see this coming Friday, October 9th, this Friday, we have Anna from Free University of Berlin. She will give a talk about the sediment routing along the Chile margin. So it's active margin system. And I think it should be a very nice talk because we'll talk about climatic and geomorphic boundary conditions. So, also next week, we have two more talks given by Steve Keel from WIMS and also Rebecca from Shellering oil company. And Steve will talk about all the sediment and the carbon delivery and preservation of the Amazon, Ganges, Brahmaputra, Ayeyarwady, and the Sovereign River. And also Rebecca, she will talk about the global delta database and also predict the delta formation on the marine coastal lines. So I think that both will be very interesting to us. So Albert graduated from Wageningen University, get the bachelor and master degree, and also PhD from Delft University, 2007, then moved to United States. And also now is associate professor and also assistant director of INSTA. So Albert now is working the high mountain river and the global warming, global change, how the sediment flux, sediment supply change. So I think I will give to Albert. Albert, please share your screen.
Thank you so much, Paul, for the introduction. Okay, so let me see. Here we go, PowerPoint. So you should see my screen now, right? Or Paul, do you see my screen? Yes, okay, perfect. So thank you very much. I'm gonna minimize this. All right. So changes in fluvial sediment supply, a global perspective. So I want to talk today a little bit about what changes we have seen in the past, but also want to look forward and what changes we're expecting. So the first part of my talk, you might have seen some findings already that are presented by Jaya Savitsky. And unfortunately, I didn't see his presentation yet, but I will get to that later. But after that, there's some new stuff, I think. Okay, so next slide, there we go. So why are we studying, how much sediment is going to the ocean? And I want to put out a few examples to show the social relevance of studying sediments. So I want to start with a coastline retreat study by Jeffrey Payne that he published in 2007, where he saw for the Gulf of Mexico a retreat of almost 2 meters per year. And one of the reasons why there is this retreat is the lack of fluvial sediment supplies to that region. Similar findings, but then looking at deltas was published in a study by Savitsky. I was involved in this, where we looked at over 30 deltas and looked at their state, right? How, what is their environmental state? How are deltas, are they still prograding or not? And we found that that almost 85% of the deltas are experiencing severe flooding. And one of the reasons is because less sediment is actually reaching those deltas. And this partly due because of building dams upstreams or channelizing channels. so less sediments actually reach the delta top. And this is important because, you know, many of the larger cities are actually at the coast, so they get impacted by these flooding events. So those are two examples where there is less sediment getting to the ocean, but there's also ample examples where you see that there's actually more sediment reaching the ocean. So this is a study done by several people. Actually, the figure I'm showing is from Restrepo. So this is the Magdalena River, and it's producing, or there's more sediment getting to the ocean, and there's actually they dug a canal or channel, sorry, where more sediment is going to the west coast, and it's hitting a coral reef there, and really the impact is devastating. It's blocking the sunlight, it's increasing pollutants, and the coral is in a badly shape because of this. So the other problem that that can occur when you increase sediments is the amount of sediments that's building up between the stop levees, and you can get a super elevation of your river bed, and therefore you have to increase the levees. But you're making, right, you're building a dangerous situation, because if a levee starts to fill, it's going to be hard to stop the water even during high discharge events. The water will pour into the backcountry. Another problem with, you know, having many sediments or an increased amount of sediments delivered to the ocean is that you suddenly have to put more money in dredging harbors or navigation ways. And this is for the US alone, this is on an annual basis, roughly $1 billion that we have seen in the last decade or so. Extra costs to dredge harbors. So, you know, how do we measure the global fluvial sediment budget to the oceans? Now, one way to do that is by going in and really physically measure the sediment concentration during various discharge events, and then establish some sort of a sediment load discharge relation. So when you measure the discharge, you roughly know your sediment load going to the ocean. Now, to maintain discharge stations is relatively expensive, and to establish such sediment load discharge relationships is quite labor intensive. So it's an expensive method, and you can imagine with, you know, so many rivers along in the globe, it's hard to constrain a global fluvial sediment budget. So the way we tackled this was by using a model, a numerical model that kind of looks at drainage basin properties, so relief, and, you know, hypsometry, river network, you know, amount of reservoirs, what kind of land use is happening on the drainage basin, and it looks at biophysical parameters, so the climate, the temperature, precipitation, evapotranspiration, those kind of things. And so what we came up with some years ago here is a global map of sediment load towards the ocean. And what you see here is actually the difference between pre-Anthropocene and modern sediment load. And where the kind of cold colors, so the dark and light blue and gray, those dots represent a decrease in sediment load if you compare the modern to the pre-Anthropocene. And the warmer colors, including the black, are where there's sediment increase, modern sediment load compared to pre-Anthropocene. And so we took the same basin properties that I just talked about and the climate variables into account. And when you do that, we estimated that for the pre-Anthropocene there was more sediment reaching the ocean than in modern days. So now, why is that? Oh, let me do one step back and just quickly tell you about how we estimate this sediment load in a bit more detail. So what the model does is it uses discharge area, a relief, and a temperature to constrain suspended sediment. And there's a B factor included as well. So we call this the Bogart equation. And it's basically a statistical relationship between what was observed for close to 500 rivers and what we predicted for sediment load. So we trained this model on 500 rivers. And then the B term includes lithology, right? How easy is it to erode the surface? It includes a trapping efficiency as well, and that's an important one when you want to look at the impact from humans. So this is trapping efficiency of reservoirs, lakes and reservoirs, and there's a human factor involved. Are we how rich is a country basically to maintain its rivers? So that's the human factor. And then we have an ice or a glacier routine where glaciers are the way we capture the glaciers is that they produce more sediment. So we look at the area that a glacier is taking up in a basin. So that's roughly. So we use Bogart to come up with a global estimate of sediment fluxes. Now for the trapping efficiency, you can see that in the last 100 years or something, humans have been quite active in trapping water. So this is a map of the US, and all the dots you see here are reservoirs. Those are roughly 45,000 reservoirs only in the US. The dots you see here are of dams that are, of a significant size. So their dam wall is close to 8 meters, and they store 18,000 cubic, or they can store 80,000 cubic meter water volume. So that's quite a bit. Let's see, next slide. So what it does to rivers is explained in this example here, that a publication from Mead and John Moody. So when the Mississippi was more or less not impacted by humans, there was roughly 400 million ton per year of sediments that would reach the Gulf of Mexico. But with the Mississippi is huge. It's draining over a third of the U.S. So it's a river. It's a significant large river. Over from 1900 till 1950 or something, there were built so many dams that only 40% of the sediment now actually reaches the Gulf of Mexico. So it really changed the regime of the river from a transport limited to a supply limited river in the course of a century. So So this from a paper from Bloom and Roberts. You can see here in the figure this what is it, light brown orange kind of colored band is the sediment supply, the sediment load that would reach the ocean in the Holocene roughly, and those lines combined here, you see a clear the degrees in sediment supply over a 30-year period or something, where the red line is a combined load of the Mississippi and the Ashevalla River, but they're all, you know, if the red line is the combined one, is still below the Holocene sediment. So what Bloom and Roberts are indicating is that a potential future scenario for the Mississippi Delta might be, as you see here on the lower right side, where there's not much remaining of the delta if you compare that to the upper right here. So New Orleans would suddenly be in the ocean here. So the US is not the only country that built dams. It's really happening all over the country, or all over the world, although the timing might differ. So what you see here is a global map where the red dots are, so the years are chipping away here on the upper left corner. And you can see that in the, like I said, in the US, it starts early on where dams are built. And especially around 1900, in the period 1900 to 1950, there were many dams built in the US, and you can see Europe starting to build dams as well. And then as soon as we pass the 1950s, 1960s, dams are built in China, India, in Africa, in South America. So it's worldwide. This movie that I showed is the Grant database, and it contains close to 7,000 dams, but there really are 58,000 large dams. It's just hard to, there's no open database of all the dams of the world. You can buy a database from ICLAW, the international community on large dams, but it doesn't contain that long. So it's kind of, you get a list of, you know, this dam is in Nigeria, but you're not sure where exactly it is in Nigeria. So it is quite hard to locate all the 50 or what is 58,000 large dams. So what dams do is they slow down the water, so the sediment get the chance to settle down and fill up the reservoir, basically. So the color scheme here is that the darker colors are where almost, you know, 80 to 100% of all the sediments that are carried by the river are trapped behind dams, and then the red is 20% lower, and so forth. So you can see that at many parts of the world, actually, dams are filtering out almost all the sediment. So it delays the water as well. So we have built so many dams now that it would take normally roughly 20 days for water to reach the ocean, and we delayed that to a 60-day period. So there is a tripling of time for the water to reach the ocean. And by all those dams, there's roughly 20% of the sediment is captured behind it. Now we're not only building dams, but we're also deforestation. Deforestation is also happening. So, and with deforestation, typically you get more erosion. So there is more sediment actually that reaches the ocean. So I'm going to play this movie again. So this is Europe, and it's, you know, I think 1,000 years BC. And much of Europe was covered by forest, where if you go just a century back, basically 50% of that forest is deforested. So you can imagine that will increase the sediment flux. So this is a simulation. This is a model simulation from Kaplan, and he did this not only for Europe but for the whole world. To see, so this is a study that also looks into deforestation, where you get a better idea about the impact it has on the sediment flux that reaches the ocean. So you see here, New Zealand is the North Island, and I looked into a river called the Waipaoa River. It's a relatively small river. For a long time, New Zealand wasn't really impacted by humans. The first humans that arrived in New Zealand was around 600 years ago. And when the first humans arrived, the Polynesian, they basically set up camps along the coast, and they had slash-burn practices. So they did cut the forest, used the land for a few years, and then moved on to another part and let the land abandoned so vegetation would grow back. That did have an impact on the sediment flux, but not all that's devastating. When the Europeans arrived, though, they started to occupy much of the land. They deforested it for sheep farms, for example. And because of the deforestation, we found a sediment load increase of between 500 and 600% increase. So 5-6 times increase of the sediment load, which you see here on the right corner graph. Similar results we found for the Magdalena River, and this is in collaboration with Professor Juan Restrepo, and I think he's going to give a talk maybe on the Magdalena. So I'm not going to tell you too much about it, other than that. So this is the Magdalena Basin you see here. It drains large parts of Colombia. When we do not take deforestation into account, we get a bad relationship between observed sediments and simulated the sediment load. But when we do take deforestation in account, we get an almost, we get an R-square of 0.8. We get a really good match. Just to say how important it is to capture those human impacts to better understand the sediment flux. And I'm sure he will talk in more detail about this. So how significant was the human impact if you compare it to other time periods? So I was fortunate to study 3 river systems in Europe. So the Po, the Rhone, and the Tet River over here. So this is France and Italy. And I looked at long-term sediment fluxes. So when you compare and these are all model simulations. When you compare the Pleistocene to the Holocene, we see a decrease in sediment flux by a factor 2.7. And this is because the Alps that you see here that are bordering the north side of Italy and Swiss, there was an ice cap on top of the Alps. There were lots of glaciers, and those when we went from a glaciated versus a non-glaciated environment, there was a lot of sediment that are actually stopped. The glacier stopped eroding the landscape, and therefore you see this decrease, and that's one of the reasons. And then if you compare the Holocene to the Anthropocene, that's where human activity came actually in by channelizing the rivers and having more reservoirs there. We saw another 2.5 degrees, so that, or a factor 2.5 reduction in sediment. So that's, so you can compare the human impact, at least for those river systems. I don't know for the whole world, but they're on the same order of magnitude if you compare what nature did with a warmer climate. And this is in contrast with, with apparently very easy erodible material, what I showed previously for the Waipaoa River in New Zealand, where we saw an increase by deforestation, just with a factor of 5 to 6 times increase in sediment load. And this might be a temporary blip. It might be that at some point those, most of the sediments are gone. You're on the bedrock, and the level of suspended sediment that reaches the ocean could be less. So this might be a time scale factor actually that we see such a high increase. So if you look at smaller timescales, and I'm almost positive that Jaya showed this figure as well, but you can see that, for various river systems, due to various reasons, could be deforestation or could be channelizing of the rivers, most of the sediment reaching the ocean. But then so for the Po River here, for example, but then building dams or having other land managed practices, that sediment increase actually turned into a decreasing again. So, and I should say this, the one-to-one line, nothing happens with a river, right? Where if you come below the one-to-one line, the sediment flux of that river is reduced, and this is years in both scales are in log scale. So that was basically, where we are at with estimating global sediment fluxes over time, and that's where we are now with our budget constraints. But if you look into the future, in the coming 100 years or so, what will change? Of course, human impact will change, right? We keep changing. Excuse me. We keep changing our landscape, but there's also climate change. So I showed already some of the impacts that humans can have. So I won't iterate more on that, but I will focus on the climate change and what that might do to sediment fluxes. And this is a study that I've done together with Seki Cohen and others. And I think Seki will talk in this session later on as well. Okay, so I want to talk a little bit about flooding. And right now, natural disasters or flooding is one of the natural disasters, but it's, if you look at the number of natural disasters, flooding takes up over 40% of all the natural disasters. It impacts many peoples, and it's repairs and rebuilding it's quite expensive. And this is a database of the last 20 years. So flooding is a world phenomena. It's happening on all continents. This is a database from 1985 onwards from the Flood Observatory that's also located in my group. So the red polygons you see here are areas defined by new sources. So this is not actually the area that's completely flooded, but the flooding did occur somewhere in this polygon. So this record is based on news outlets where it was described, Houston and suburbs were flooded, and then we draw a polygon around there. And so with climate change, does does flooding change, and how does flooding impact the system? Now, well, you can imagine that if you got flooding, you have you have different erosion patterns, right? There could be bank erosion because of flooding, but there could also be sedimentation due to, like you see here on the right, due to crevasse place. So we want to see what if flooding changed, if that also changed the sediment fluxes downstream. So do we see a change in flooding? And this is, you know, it's kind of hard to capture all the floods. So it's, to look at a flooding database alone is, I think, not enough. So I looked also at precipitation records. Now for temperature, we know pretty sure there is a temperature increase, right? But rainfall is a little bit harder to measure accurately. For various reasons, but NOAA was able to constrain a global precipitation anomaly database, which you see plotted here from for the last 100 years, basically, where the light blue line is the annual anomalies, and I've done a 9-year running average. So when you look at that line, you can kind of see an increase in anomaly precipitation, right? Where if you are on the 0 to 0 line here, there's no significant increase or decrease. If you're below that line, there's less precipitation that year. So you can see an increase there. So when you look at the extreme one-day precipitation events, and this is this plot is only for the lower 48 states. So this is not a global data set. The previous was, but this is only for the United States, and it looks at the percentage land area that's affected by a one-day extreme precipitation event, and you can see that there's not much difference for the till 1980, 1990 or something, but then there's, well, from the 1980s onwards, there's kind of an increase in percentage land area that's affected by an at least one day extreme precipitation event. And so when you look at the DFO Flood Observatory flood record from 1985 onwards, we make a differentiation between large floods and extreme flooding, and I can go into detail later if there are questions about it. But how to come up with what is a large flood, what's an extreme flood? But when you look over those last 35 years or so, you see an increase in the number of large floods. And you see even an increase in the number of extreme floods. And those are, this is still based on that news database record. So it could also be that, in the early 80s, there was less coverage by news agencies. So this is not a very reliable source, but it's an indication that floods are increasing. Now, do flood frequency does the flood frequency change in future or not? And does the magnitude change? And are there different areas on Earth that are affected by flooding? Now, to study that, we looked at, we calculated flooding based on a log Pearson 3 distribution of discharge data. And for discharge data, we used actually a model. So you can estimate recurrence intervals, right? How often does a certain amount of, or a certain water discharge occur? And you can imagine that, you know, when you got a 1 in 100-year flood, there's a lot of discharge running through a river, but it's only statistically 1 in 100-year, right? Skip that. So we used to estimate it. We used something called the water balance model. It's a model by Charles Forest-Matty and Balázs Fekete. Let's see. It's a global model. It takes into account many components of the water cycle. So it takes into account groundwater. It takes into account reservoirs, water uptake by humans, and all that kind of things. It's a 2D model, so it's routing water over the land. I won't talk more about the model. I'm sure Seki will handle that, but I'm going to focus on the study here. So we used IPCC AR5 for future climates, to get precipitation as well as temperature input. And we specifically we used the HEDGEM 2ES simulations for this, and we focused on the RCP 4.5. So it's a somewhat conservative pathway. So we didn't look into the extreme extreme climate change. So this the RCP 4.5 assumes that we got a CO2 peak around 2040 and then a slow decline. So a temperature increase of close to 2 degrees Celsius. So for the model simulations, we only took changes in climate into account. We didn't look at land use changes. We didn't look at potential new locations where dams could be built or anything like that. We only focused on how the climate could by itself impact the amount of flooding. And we looked at 2 30-year periods. So for the future, from 2070 till 2100, and for current from 1975 till 2004. And basically we set up those, the recurrence intervals, the recurrent discharges for each grid cell. So a grid cell is, I think, just a little bit over 10 square kilometer. And when it captures a river, you can, based on the amount of the 30 years of data, you can construct those recurrence intervals with the log 3 Pearson. And so each recurrent interval, you estimate you get a discharge, and so you can construct something like a global map for bank full discharges. So bank full typically, right, that there's no flooding, but the water is right at the edge of the levee, natural or human-made levee. Human-made, I guess not. So once you have a larger discharge, you know that the river will flood. And we used those peak discharges then to look at the future simulations, that 30-year period, to see if there were more frequent high discharges. And so you can make some sort of you can estimate the number of days when a river is in a certain discharge interval. And so this is the future simulation compared to the present day recurrence intervals according to the model. So this is all the discharges that have a return interval higher than 2 years. So that means flooding. And you see that for the areas that are in red, there are typically less flooding there. And the areas in the colder colors, in green and blue, there's more flooding. There's a flooding increase. So the number of days that we measure discharge is higher than the return interval of 2 years. Those show up in the blue colors. So this is a map of the world where you can see that's kind of West Europe or East Soviet Union. It looks like there's a decrease in flooding. Same for the East Coast, for example, of Brazil, for the Amazon River, Orinoco there. But we do see increases as well in the hinterland of the Amazon River. There seems to be more flooding. Middle parts of Africa, along the east coast of the US and Asia is lighting up with more flooding as well, it looks like. And if you look at only the recurrence intervals of the 100-year return flood, right, the larger flooding events, you can still see that there's an increase in the hinterland of the Amazon, and also Asia is showing up. So when we estimate for the various continents how flooding will change over time, it looks there's an increase in flooding for all the different return intervals, except in Europe maybe where there are less small flooding, but the bigger flooding events, there are more big flood events, and this is a percentage change number of days. So there's for many of the larger floods, there's 100% or more chance that flooding will occur there. Yeah, touch based on that. So to conclude on the flood frequency, we do see a change, and for some cases a doubling or more even in the number of days or of flooding. When you look at the percentage change, let's see, for large flooding events, when you normalize your distribution and you look at, are there percentage-wise more large events versus smaller events? If you compare it, what's happening now into the future, there you see also an increase in the magnitude of flooding. So therefore, according to our model simulations using the climate forecasts or predictions, we do see an increase in the magnitude of flooding as well. And then for spatial changes, so this is a map where if you see the light, it's not very clear, maybe the color scheme, but the light yellow here is areas that are flooded or where flooding occurs right now, but also for 2100, where the blue areas are flooding currently, but not in 2100, and the red areas are flooding only in 2100, but not currently. So you do see a shift, here again for Europe, where there looks like there's currently more flooding when you compare it to future scenarios. I'm gonna skip the summary. I want to touch base on one more study. Oh yeah, I do want to say one thing about this. So the method we use to estimate global sediment fluxes, we use the Bogart equation, right? That uses discharge, area relief, and temperature to estimate suspended sediment load. There's no flooding component in there, so changes in flooding doesn't show up in the equation itself. So I think we need to modify make modifications to the equation to be able to capture such changes. And just to show you that flooding is important, according to Ellison in 2 studies, he showed that on the floodplains of the Ganges-Brahmaputra, most of the, or 40 to 70% of all the river sediments is actually trapped there on the floodplains. And similar for the Mississippi, he found that over 40% of the suspended sediment load is captured on the floodplains. So flooding is an important process. And we should take it into account, I think. I want to touch base on one more study that was done in collaboration with Dongfeng Li and Professor Qiqi Lu. And I know Professor Qiqi Lu will most likely present this in more detail to you. But I want to highlight 2 little points, and I'm sure he will do a better job. I think he's scheduled for April. So I do encourage you to go to his talk, because this is quite quite a nice study and a unique data set, I think, that they present. So this is about permafrost and how temperature controls processes in permafrost and what it does to the suspended sediment load of rivers. So to study this, they use data from the Tutui Basin, which is located at the Tibetan Plateau. So that's the headwaters of the Yangtze, right? It's high elevation, so continuous permafrost area there. And the data set is a 30-year daily observations of water discharge and sediment load. So 2 things I want to touch base on, and one is the changes actually in contributed area to so your drainage basin, basically, that can deliver sediments. So you can imagine that when your area is completely frozen, there's not much free sediments available to transport downstream, right? So I've tried to capture this, and I'm pretty bad in drawing in using some programs here. So anyway, the white is say permafrost area. So your drainage area, although it might include the mountains upstream and then the lower lands, if it's completely impacted by permafrost, there are not much sediments that move. So the active drainage area is the lower area here, and that's what you can observe, for example, in wintertime, where in summertime this permafrost region has its active layer becomes thicker, and an active layer is not frozen anymore, so particulates can move and can move downstream. So and that's what they found, or that might explain that mechanism. When you increase your area for seasonal changes, you can also see the sediment load is here on the y-axis, and the basin area is on the x-axis, and you see the sediment flux increases with seasonal changes, and we think this is due to changes in the active drainage area. And then the other thing I want to touch base on is actually that active layer itself. So during the winter time and early spring, the active layer is completely frozen, right? It's permafrost. But then when you get more towards the summer season, your active layer here colored in this light light red color, orange color, that becomes your active layer where sediments can move and water can flow through. And at some point, actually, there's the water sinks all the way deeper into the active layer. So you have the top layer where it's dry soil and less particles actually can move. And you can imagine, so your sediment curve, and this is sediment concentration, not sediment load, and water discharge here. So you can imagine that, you know, your active layer becomes more thicker, and therefore more sediments can move, and you see an increase in sediment concentration here over the seasons. But at some point, you hit your dry soil where there's less transport, right, mechanism. The water is not there anymore to move sediments, so you get a decrease again, and then the winter starts and the soil gets frozen again, and you get to very low sediment concentrations. Now you can imagine that when you got climate change going on, those seasons will actually will be larger, right? The summer seasons, it will be warmer, and therefore your active layer becomes thicker, and that will have an impact on the sediment concentration. Now this is only a study for the Tibetan plateau, but you can imagine that, you know, large parts of Alaska might be impacted by similar processes. And for the active contribute drainage area, you can think of Greenland, for example, right, where there's a big ice cap right now, but if that will go, there's more ground underneath it, or at least at some parts there's ground underneath it where more erosion can occur. And with that, I'm going to stop, and sorry it took a little bit longer than I expected, but thank you very much for listening.
Thank you, Albert. So let's see if any question here. So on the chat, Albert, are you able to click the chat?
Yes, so let me,
the chat,
hold on.
Sun Shuang.
Yes.
Is it, you know, thanks a lot for the presentation. I have a question about the deforestation. Do you know how to distinguish the vegetation coverage controlled by climate and human activities? Because the result of vegetation coverage are affected by two factors. So. Yeah,
no, very, very good question. And totally true. This is a difficult one. You know, humans control vegetation cover quite significant, I think, and we basically are changing the world into a parkland, right, where we determine what kind of vegetation is growing, and climate for sure has a control on it, especially when you get to the more arid areas where there's less water for vegetation to grow. It will be, you know, once you remove the vegetation there, it will be challenging to get vegetation back. But in the more humid areas, I think it's humans that really control the vegetation cover. So I think for vegetation, I would look at the human dimensions, and you know, that there might be simulations of how future changes of land use will occur, and I would think humans have a bigger impact there than climate. But yeah. Thank you for that question.
Okay, but you know, that other question from Edlik, you know, I think from Malaysia. So Edlik, the question is, in your global model for flooding according to R equal 10 or higher, how do you account for the fact that the rainfall intensity is not the same from basin to basin?
Yeah, good point. So we used a global precipitation product, and that's a gridded product. So it has, you know, the grid cells each have their precipitation. So it could be very intense on a single grid cell, but on the other grid cells there might be less intense rainfall. Now, when we look at flooding, we also look at so for those recurrent intervals. So RE equals 10 means there's flooding, right? Every statistically 10 years there will be flooding, but it will be flooding at that grid cell. So we don't look at the whole basin, but we look at that single grid cell where of a larger basin. So it could be a small river reach as part of the Mississippi River that's affected by flooding, but not the entire Mississippi is necessarily to be flooded. So I hope that answers your question, Adlik.
Okay, is there any question? If people have any question now, you can unmute yourself now. So directly ask any question if you have. So,
oh, and I see. Okay, so Anna has a question.
Yeah.
I have a question on the influence of vegetation cover on sediment load. Do you have a sense how the type of vegetation influence river sediment load? For example, vegetation with deep roots, trees, versus vegetation with just shallow roots, grassland. Excellent question, Anna. When this was one of the harder things to capture in our model exercise, because there's not much data available on that study different vegetation types and how much erosion takes place. So we did found a few studies in Africa, in Spain, that looked at plot scale, and those plots could be quite large, right? Several hectares or something, but not like a river basin. But they looked at they described the type of vegetation, but predominantly grassland or predominantly forest, and then they indicated how much erosion took place, and it included lithology and those types of things as well. So we had an indication of how easy is it to erode the landscape, and we knew the types of vegetation. So that's how we constrained our sediment budget based on different vegetation types, and that's what we did actually then apply for the study in New Zealand, the Waipaoa River, as well as for the Magdalena River in Colombia. Now, I would, if there are more studies, I could not find that many studies on erodibility versus vegetation. If somebody has more references to that, I would welcome those. It would only strengthen the models. Thank you.
Okay, that's good. So Adlik, I have other question. Before we shift to his question, there's a comment from Will Borcher. He said he learned a lot. He said a very interesting effect. Your presentation, to me at least, very novel in my limited experience, and also really comments a great talk. And Alec's question is, how about the verification of your global models?
Yeah, good point. And I didn't touch base on that, assuming that Jaya would have done. So actually, I said that. So we used what was it, 488 rivers or something to constrain. So to train the model, basically, right? You have your impact factors on one side, and the sediment load. So we constrained this Bogart equation based on 488 rivers. But then there was an additional data where we actually we did not use, but afterwards we were validating our model to see how well our model could simulate the suspended sediment load. So we used a different data set for that. and I forgot the number, but it's published in this Journal of Geology, Savitsky and Milliman 2007, I think, paper. So that it will talk about how the model was developed and how it was validated. But we had a separate data set that we did not use to develop the model, but then validated the model with.
Okay,
thank you,
Albert. So I have a question. Here you mainly talk about how much water, the potential flooding, and also how much sediment coming down. Do you know anybody now working on global scale about some geochemical element, the global scale, the change? For example, last week, Edward Taper from University of Cambridge, he talked about silicate weathering, global scale. That's very good. And how about those clay mineral, is any kind of historical change? So far, most of the geologists, including the people in this group, we look at clay mineral, each river, just like a snapshot. And anybody do that kind of global scale historical change work?
There's so much to study still, Paul. I think
maybe our next generation, our next life.
Yeah, that's something. No, I have not looked into that. It would be magnificent. It would be great to have such a data set.
Okay, maybe we can talk even in some audience. We can think about maybe a next project. Put a global scale data. Look at how much of the phosphate, nitrate, any kind of the nutrient global scale change. I know individual river basin people have some work, but put them together.
There's a model called NEWS. It's developed by Emilio. No, I mispronounced his name.
Mm-hmm.
The model is called NEWS, and they have done some, phosphor, nitrate, global fluxes towards the ocean. We thought actually it would be kind of low-hanging fruit and easily to establish, to incorporate something like that in our sediment budget as well, because there is a relation between sediment and many of those nutrients. Actually, but we were not able to pursue any funding to do that kind of research.
Okay, very good. So thank you, Albert. So if you know any other question, I would like to see again this coming Friday. Anna from Free University of Berlin will talk about the active margin, the Chile margin. So I think it will be a very interesting talk, combined the impact, the effect of the climate and the geomorphology change. And also next week, Stu Keel and Rebecca still talk about also all the way from Amazon, Ganjaboma, Potra, Ayawadi, and also Rebecca talk about the global delta data set. And I think all our talk will be great, fantastic. So once again, and this talk is also recorded on the YouTube. So if you like to carefully study each slide, you can go back to rewatch. And I will check to Albert. Maybe later he will share the PowerPoint slide to this community. So for people to to study more carefully. Okay, if no other any question, so I think Albert, thank you very much, and our audience, thank you, everybody, and I see you this coming Friday and also next week. Okay.